the compound angle formulas. I'm going to create them by using my unit circle here. Radius 1. There's a point P. If I drop a perpendicular down, and let's say that angle is beta. Okay, let's look at that triangle. I can work out the y coordinate and the x coordinate, if you like, effectively finding the parametric coordinates of the circle. Now x over 1 is cos beta, so the parametric for x is cos beta, and for y is sine beta. So it's in terms of the parameter, that being beta. But that means any point on there can also be represented parametrically. So over there, the point Q, let's say that angle's alpha, so parametrically that would become cos alpha sine alpha. What I'm interested in is the distance between P and Q. I could do it using the cosine rule. So I could use trig. So PQ squared, 1 squared plus 1 squared minus 2 times 1 times 1. The cosine of whatever the difference between those two angles is. Tidying that up a bit. But I could also use coordinate geometry and use the distance formula. Now I know that the difference in the x values squared plus the difference in the y values squared would be PQ squared. Pythagoras' theorem, basically. Expand all that out, and you'll notice we've got some cos squareds plus sine squareds, which we know is equal to 1. So all of that tidies up to be 2 minus 2 cos alpha cos beta minus 2 sine alpha sine beta. Yet they're both equal to PQ squared. So these two expressions must be the same. So the reality is I wasn't actually interested in the length of PQ. I was actually more interested in this expression. Because from this, playing around with it, I now have an expression which allows me to expand out, if you like, trig. See, it's not like algebra where I can say, well, the cos of alpha minus beta is the cos of alpha minus the cos of beta. We're not really expanding out the parentheses. We have to use this pattern. The cos of alpha times the cos of beta plus the sine of alpha sine of beta. Now what I'm going to do is I'm going to replace beta with negative beta. But I now have a formula, which means alpha minus beta becomes alpha minus minus beta, alpha plus beta. And over in the other one, we have cos alpha cos minus beta, sine alpha sine minus beta. But I know cosine is an even function. So the cosine of minus beta is the cosine of beta. And sine is an odd function. So the sine of minus beta is minus the sine of beta. Substitute that in. I now have a way of expanding, for want of a better word, the cosine of alpha plus beta. And if we look at them, they're very similar. So here's a way of remembering it. Cos, cos, sine, sine. That's the pattern. Cos, cos, sine, sine. But how do I know whether I'm going to go plus or minus? Well, if it's not the sine, no, not the sine. It's cosine, it's not the sine. Then it's not the sine. So it's not the plus, it's the minus. It's not the minus, it's the plus. You see? So cos, cos, sine, sine. If it's not the sine, it's not the sine. Now, I'm going to go back to that first one, but this time I'm going to replace alpha with 90 minus alpha. Substitute that in. I'm going to play around with complementary ratios this time. If I just group the first one, that 90 minus alpha minus beta becomes 90 minus alpha plus beta, and we know sine is the complement of cosine. So we end up with the sine of alpha plus beta is equal to sine alpha cos beta plus cos alpha sine beta. But in that one, I'm now going to replace beta with negative beta. Once again, I'm going to use the fact that cos is an even function and sine is an odd function. And look what we get. Again, they're very similar. So that pattern goes sine, cos, cos, sine. But if it's the sine, it's the sine. We don't change the sign this time. Cos, cos, sine, sine. If it's not the sine, it's not the sine. And sine, cos, cos, sine. If it's the sine, it's the sine. But see, how do you remember this? You always start with the same ratio. So when it was cosine, I started with cosine. Cos, cos, sine, sine. When it was sine, I started with sine, so sine, cos, cos, sine. But then the other thing to remember is you always say cos, cos. So as soon as you say cos, you've got to say cos. So with cosine, it was cos, I said cos. Cos, sine, sine. Where with sine, you go sine, cos. I said cos. Cos, sine. See, you always say cos, cos. Alright, time for tan. Tan, of course, we could rewrite as sine on cos, but that's not a problem now because on the top I have sine, which is sine cos, cos sine. If it's the sine, it's the sine. And on the bottom I have cos, which is cos cos sine sine. If it's not the sine, it's not the sine. So I have this expression. So what I want to do with this one is to simplify it by making it look more complicated. I'm going to divide everything by cos cos. That wonderful expression again, cos cos. But look what happens in each fraction. We get some cancelling. Look at the very first fraction. Cos beta cancels. I'm left with sine on cos, which is tan. I end up with tan alpha plus tan beta on 1 minus tan alpha tan beta. Replace beta with negative beta. Let's see what happens with the negative one. Tan. That's an odd function. And we get that. So this is what we've got. Tan plus tan on 1 minus tan tan. Tan plus tan on 1 minus tan tan. To summarise our formulas. Sine. Sine cos cos sine. If it's the sine, it's the sine. Cosine, cos cos sine sine. If it's not the sine, it's not the sine. Leaving us with tan, which is tan plus tan on 1 minus tan tan. Our compound angle formulas. Remember it this way. It's a bit like, you know, how I told you how you think about the product rule and the quotient rule. Because basically you're writing down what you're saying. So it's the way, I'm just writing it down as I say it, and you get the answer. So if I now want to, for want of a better word, expand cos 2 alpha minus 3 beta, not a problem. Cos, cos, sine, sine. If it's not the sine, it's not the sine, and there's my answer. Simplify this expression. But you look at it and go, hang on, it's tan plus tan on 1 minus tan tan. Therefore, that's the same as tan 20 plus 10, which is of course 30. That's tan 30. The pattern. Noticing the pattern. Tan plus tan on 1 minus tan tan. That's 1 on root 3. Find the exact value of sine 15. Okay. Well, we have exact values for 30, 45, 60, and the boundary values, so 90 and so on. How do I get 15 out of those numbers? And there's different ways I could do it. Which way did I go? I went, 45 minus 30 would be 15. I mean, I could have said 60 minus 45. I mean, it doesn't matter. Sine. Sine, cos, cos, sine. If it's the sine, it's the sine. Then we substitute in those ratios that we know. Tidying that up, we have an exact value for the sine of 15 degrees. They've told me sine alpha is 2/3 and cos beta is 1/4. They want us to find the sine of alpha plus beta. Well, I'm just going to draw up triangles here so I can read off them the ratios. Sine alpha is 2/3, bit of Pythagoras, the other side's root 5. Now, don't make the mistake of thinking these angles are in the same triangle. I mean, clearly they're not, because the cosine of beta, how would I get 1/4 out of that? It's a different triangle, the other side's root 15. Sine is sine cos cos sine. If it's a sine, it's the sine. But now I can read off my triangles, substitute in, and get my answer. 2 plus 5 root 3 over 12. Ooh. Find the tan of the inverse sine of 2/3 plus the inverse cos of 1/4. Remember, these inverse trigs are representing angles. So it really is just saying the tan of alpha plus beta. So if alpha is the inverse sine of 2/3, I'll draw myself up a triangle. So the sine ratio is 2 on 3, other side's root 5. And I'll say beta is the inverse cos of 1/4. Draw up a triangle for that one. And there we go, root 15. Tan plus tan on 1 minus tan tan. Substituting. Play around with that one. And eventually we get an answer. There it is. 2 plus 5 root 3 on root 5 minus 2 root 15 for our answer. Alright, now we have some fun. Okay, 17D, our compound angles.